Thanks for the opportunity. I'm here not only on behalf of Tata Steel, also our colleagues from POSCO, Korea, another steel company are there. We joined already quite early with heart as Tata Steel, looking at an opportunity to collaborate for new markets for steel, but also helping a startup further. And basically that has continued. So at the moment we do have a formal collaboration also between Tata Steel and POSCO on developing, and in Berlin we presented some of that. Also in Busan there was a presentation from the POSCO side. And basically, quickly summarizing, then I can skip my first slides, we have two lines where we see the collaboration running. One is you have to develop other steel grades to suit really the Hyperloop needs. And now there is something, yeah, great. And the other thing is, we also think that if you really want to make a sustainable Hyperloop, you need to come to different designs. You need to lightweight the structures. And I'll dive in a bit more in that detail. Thank you, Martin.
You're welcome.
Well, starting with a very nice picture, this is very close to my holiday home. It's the header in a nice evening. And I think even there you could have a Hyperloop without disturbing the circumstances. So that was my tube design. As I said already, we are two big steel companies and we see a market. And here also the theme of collaboration is essential. Because in the end, the market can be so big that no single steel company can do it. Actually, even together we couldn't do it. So we said we better develop and invest in intellectual property, and from there start on and build this market and help these new technologies to reach the market. I'll quickly go on. And as I said already, what is happening? Yes. Infrastructure is a big part. It's a huge cost, probably the biggest cost. The pots will be expensive, but they're smaller in total cost. That infrastructure will be there for decades, so what we choose now should be really good. But also building time should be relatively short. You don't want 5 years of disruption in a city. You want relatively quick installation, and we look to that sort of thing. So there we come to our conclusion that steel is a quite optimal material for many parts of the tracks. And we developed already a few steel grades which have additional dampening, so that if you have sound waves traveling through a tube, you actually dampen them more effectively than in normal steels. That was presented last year, and now I want to go to a bit more design. But first, a little bit more on the steel side. The reason we think steel is very optimal is it is in the end fully recyclable. You want this infrastructure to be long-term in place, but eventually it will be demolished, renewed, repaired. And also the steel industry as a whole is really trying to innovate and reduce its CO2 emissions, with all targets going to zero CO2 emissions in the future. So I think that can nicely come together with objectives that Hyperloop has. It is already also for tubes, in regular tubes, you see these tubes that are actually going to Groningen. These are tubes made from the steels that we just said, and they are on the way to Groningen, and I think next week you will install the first 2 of these. But this is made with standard technology. So making these big tubes are standard factories, which helps acceleration of implementation if needed. Well, further on, steel has good properties as air tightness, which is logic. It's relatively durable, but also things like heat management. If you have an insulating tube and there's heat generated in the tube, there is an issue, because in vacuum it doesn't dissipate, while in a steel structure you still have some power of dissipation. And you can later also make modifications relatively easily. You can weld, you can cut it, you can open up, make new safety facilities or whatever more. So we think it's well matched, and also the electrical steels used in the system are relatively well matched with the steel structure then, so you don't have too big differences. And if we then think about how we're going to innovate, not only in the steel but in the tubes, well, it's lightweighting, as I already said. Less weight is easier to install, but it's also lighter foundation, so you get a cascade effect. The total system can get lighter. You still want very stiff and stable structures, because especially under the dynamic loads that you get, obviously you don't want the structure to deform. We think that is quite well possible with steel structures. We've done quite a lot of modeling on that as well. Heat dissipation I mentioned. One aspect which for more materials is there, and Lucien this morning already mentioned, or in a discussion, to have solar panels on top of the tubes. Temperature difference between the top and the bottom of the tube are actually one of the biggest challenges in the forces that you have on the tube. The The expansion differences seem small, but if you calculate it over long lengths, it's really one of the issues that we are working on to tackle. And then manufacturability. If you make a very complex tube, it's more difficult to fabricate. So you have to balance that in cost of production whilst cost of installation and lightweighting. So that's sort of parameters that we use. And if you then look to traditional tubes, basically, if you look to the picture on the top right, if you have a tube with a vacuum inside, you could see it's compressed. And as you know, if you have like a Coca-Cola can, if you compress it, it starts to crumble. Well, that will also happen with a tube that you suck vacuum if it's too weak. It will actually buckle and collapse. That's a failure mode under the vacuum. And you have to have the long length. So there's combined forces actually lead to buckling. And one traditional way to solve that is to use awfully thick material. So as an example, for a 3.5 meter diameter tube, you would like to use around 20 millimeters, so 2 centimeters thick steel, which is doable, but it's a lot of steel, so it's a lot of weight. And we've worked on innovative designs where basically by folding, you could say, you create virtual thickness in the wall, or, that's the design I'll come later on, you separate the function of maintaining the vacuum, which is actually, you only need a very thin skin, and the stiffness into different substructures. That makes it more complex, but it is actually working, and then you get to a sort of skeleton structure, and that's the picture here on the top right, where basically you have a skeleton, and the skin, it's this bit, is actually not under compression, but if you design that correctly, it's under tension. And steel operates very well under tension, so you don't buckle. You have the structure, that's the frame, and that's the skin is actually sort of under tension in that system. And that can work pretty well. And what we've calculated in finite element modeling, but also in really building these structures, that you can reach reductions in weight of over 50%. And that's quite considerable if you calculate that over a track of 500 kilometers. So it's really interesting to follow up on these things. And, well, basically also to bring it even closer to you, it's not such a novel idea. If you take these sort of very primitive Indian canoes, which were a frame with deer skin over it, they use exactly the same principle. Because what you have here is a frame that provides the strength, and this is a nicer one than maybe the Indians had, but the skin is actually very thin. It's pressed towards. It's also, well, it's not 1 bar difference, but it's a pressure differences over a membrane. And the canoe works perfectly fine. Well, we have a bit of a modern canoe, where you have, and it's not very visible in the not-so-light picture, you have the frame with the rings and stiffness along the length. And actually that has the same sort of function, which we'll be able to make. So for us, together with our friends from POSCO, the next steps I started with the longer term. We are still working on different concepts to even go further down in weight and still have a safe thickness in the skin. In the end, we have had designs where you could go to 0.15 millimeters, so really thin material even works. But then someone comes along with a screwdriver and punches a hole in it. I think that's not the option. So there is a balance between how rigid, how solid the system should be, and lightweighting. So we are designing new concepts there, ensuring they're all possible to construct and make easily, maybe even on site, because that makes transport a lot easier. And calculate, and we would like to do that really with a lot of partners, what the eco-impact is of different concepts, also other materials. I mean, we should not exclude there also concrete tubes, and maybe in some areas there are advantages, if you have a tunnel or whatever. So we have to compare these different things. On the short term, we will engineer one of the concepts, the skeleton that I just showed, fully to a full-size system, which we also hope to integrate in the European Hyperloop Center. I used HDP here, a Hyperloop development program, but it's the EHC that should be there, to really have one segment in that tube once it's running up in Groningen, and then test how that works under dynamic load, under the real loads, and from there build on to more systems, maybe different designs, and optimize the system really fully. So, concluding, We really support the EHC in the Netherlands, but also with other partners. We have discussions to see how we can help each other. I didn't mention it earlier when you asked, Martin, but also our colleagues from Tata Steel India do have collaborations with the Indian startup side, and there is not full, but there is quite some exchange there as well. So we supply steel for switches, for tracks. We go forward also with new types of tubes in the EHC, and the combination of these steels and in the end the designs, I hope, will also boost and make some of the developments of the whole Hyperloop community possible. Because in the end, if your infrastructure becomes 50% lighter, it becomes also probably a lot more affordable. And I think that balance is what we need to strike. Have a solid system, does the job, but it shouldn't be over-dimensioned and horribly expensive. Thank you all for listening.